Derivatives of trig functions, part 1. Here is a group of trigonometric limits to memorize. Each one of these can be derived using the squeeze theorem. I won't expect you to be able to derive these limits, but you want to make sure that you have them memorized because we're about to apply them to evaluate a whole bunch more, slightly more complicated limits. So if we have the limit as x approaches 0 of sine of something over that same something, that will be equal to 1, as long as, of course, theta is some sort of function of x. It has to be in terms of x. So in order to evaluate the limit, the angle, so your sine of whatever your sine is of, and the denominator, or the numerator, if we have the reciprocal, need to match each other. Here we have the limit as x approaches 0 of sine of 3x over x. So we need this 3x, the angle, and the denominator to match each other. The thing is, changing the inside of a sine function is going to be pretty tricky, but changing the denominator of a fraction isn't too bad. We just have to multiply by the same numerator and denominator, and we'll be okay. So that means that we're trying to change this x into a 3x. So this is equal to the limit as x approaches 0 of sine of 3x over x, and then in order to change an x into a 3x, we multiply by 3. And if we multiply the denominator by 3, we best multiply the numerator by 3. So this 3 will join us for a 3x, and this 3 is in the numerator is kind of left over. But this will be equal to the limit as x approaches 0 of 3 sine of 3x over 3x. And now we're really close, but we have this extra 3. So we're going to use limit laws to pull that 3 out. So this will be equal to 3 times the limit as x approaches 0 of sine of 3x over 3x. And now our angle and our denominator match, so we can use the limit that we have memorized. So this whole limit here will evaluate to 1. So this is equal to 3 times 1, which is 3. We have the limit as x approaches 0 of tangent 2x over x. For the limits that we know, they all involve cosines and sines. So we'll have to rewrite this limit in terms of sine and cosine of 2x. So we have the limit as x approaches 0 of tangent 2x is sine of 2x over cosine of 2x. And then I have this division by x, so that's 1 over x. And now we want to split up our trig functions so that we can try to figure out which of these known limits will be useful. I'm going to pair this x with this sine of 2x because one of those known limits has sort of like a sine of x over x. So this is equal to the limit as x approaches 0 of sine of 2x over x times the limit as x approaches 0 of 1 over cosine of 2x. So I just use limit laws to split up the products of these functions. Now for my limit as x approaches 0 of sine of 2x over x, I'm going to need to get these to match each other. So I can't really change the 2x inside of the sign of x very easily, but I can make an x in the denominator a 2x by multiplying by 2. So this will be equal to the limit as x approaches 0 of sine of 2x over x, and then I'll multiply by 2 over 2. And this will be times this guy, but this doesn't really look like one of my known limits, because although I have this cosine of 2x, I'm not subtracting 1. So let's just see what happens when we try out direct substitution for this piece. So that'll be 1 over cosine of 2 times 0, which is 1 over cosine of 0. So now this is equal to the limit, well, hold on, so this 2 will go over there, and then this 2 is extra. So I have 2 times the limit as x approaches 0 of sine of 2x over 2x times 1 over the cosine of 0 is equal to 1. So now I have 2 times, this is now in the format of one of our known limits, and it is equal to 1, so I have 2 times 1 times 1 from that 1 over 1. So that is equal to 2. And that is what my limit evaluates to. We have the limit as x approaches 0 of 1 minus cosine x all over sine x. So let's start by splitting up our functions. So we have the limit as x approaches 0 of 1 minus cosine of x over 1 times the limit as x approaches 0 of 1 over sine of x. So these look pretty similar to our known limits, but we need this x and the denominator, and this x and this numerator to match. So this will be equal to the limit as x approaches 0 of 1 minus cosine of x over 1, and then we have to multiply this by x over x times the limit as x approaches 0 of 1 over sine of x, which also needs to be multiplied by x over x. This x will follow, this x will be extra, this x will join that limit, this x will be extra. So then we have the limit as x approaches 0 of, well, x is a function, so we'll have to give those their own little limit here from these extra x's in the numerator and denominator. And that will be times the limit as x approaches 0 of 1 minus cosine of x over x times the limit as x approaches 0 of x over sine of x So the limit as x approaches 0 of x over x, because these x's divide out to 1, will just be equal to 1. So we have 1 times the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. times the limit as x approaches 0 of x over sine of x is equal to 1. 1 times 0 times 1 is equal to 0. So that is what our limit evaluates to. We have the limit as x approaches 0 of tangent 4x over sine of 5x. So let's first rewrite our tangent. So this will be equal to the limit as x approaches 0 of sine of 4x over cosine of 4x times 1 over sine of 5x, so that we have that division by sine of 5x. And then we'll want to split all of these up. So this is equal to the limit as x approaches 0 of sine of 4x over 1 times the limit as x approaches 0 of 1 over cosine of 4x times the limit as x approaches 0 of 1 over sine of 5x. For our sine of 4x over 1, we'll need that denominator to be 4x. For the limit as x approaches 0 of 1 over cosine of 4x, that actually doesn't need to be changed because cosine of 4 times 0 will give us 1. So that actually evaluates to something that works. For our limit as x approaches 0 of 1 over sine of 5x, we'll need our numerator to be 5x. So this will be equal to the limit as x approaches 0 of sine of 4x over 1 times 4x over 4x times, we'll use direct substitution to evaluate this. So we have 1 over cosine of 4 times 0 times the limit as x approaches 0 of 1 over sine of 5x times 5x over 5x. This 4x is necessary for that limit, but the 4x in our numerator is extra. This 5x is necessary to evaluate this limit, but this 5x in the denominator is extra. So now let's pull out some pieces of this. So we have the limit as x approaches 0 of our extra 4x over our extra 5x times the limit as x approaches 0 of sine of 4x over 4x times 1 from our 1 over cosine of 4 times 0 times the limit as x approaches 0 of 5x over sine of 5x. For our limit as x approaches 0 of 4x over 5x, these x's will divide out. So we just have the limit as x approaches 0 of 4/5, and the limit of a constant is that constant. So we have 4/5 times, well, the limit as x approaches 0 of 4x over 4x looks like one of our known limits. So this will be equal to 1. Then we have our times 1, and then we have our times the limit as x approaches 0 of 5x over sine x, which also looks like one of our known limits, and evaluates to 1. So we have 4/5 times 1 times 1 times 1, which is equal to 4/5. So our limit evaluates to 4/5.